Today we are going to discuss differential equation, specifically partial differential equation. But before that, we need to know some formulation in order to derive a solution of some differential equation, whose are particularly ordinary differential equation. So for this, we will first look at the equation of type n is a function of t, and where we will see where while we're differentiating n with respect to t, let's say this is equal to some constant lambda minus lambda of nt. So if we integrate this, if we take the integration side, dn by n, because we will use the separation of variable, and we will integrate both sides. Integration of dn by n is equal to minus integration of lambda dt. Then we will get ln of n is equal to minus lambda t plus c. Or we will get ultimately the solution as n is equal to n naught e to the power minus lambda t. So this is a solution of ordinary differential equation, which will be very useful in order to solve partial differential equation when we will solve the partial differential equation or convert partial differential equation into ordinary differential equation. Then we can use this formula. So now this is again homogeneous equation. This is again ordinary differential equation. So the first order ODE or ordinary differential equation, m of the function m is of x and y, and with dx plus nxy of dy is 0, is homogeneous. And how we will know that it is homogeneous? If m of xy and n of xy are homogeneous function of the same degree, or if it can be put in the form y dash is equal to f of y by x, then we can put y is equal to vx. So we can basically we can substitute y is equal to vx, and then we can ultimately get into a form where y dash can be written as function of y by x. Then that equation will be called as homogeneous equation. What are the conditions for exact equation? If m of xy dx plus n of xy dy is 0, it will be exact if this m xy dx plus n xy dy is exact differential of the df of xy. And the necessary condition and sufficient condition for this equation to be exact is partial of m with respect to y is equal to partial of n with respect to x. Now we need to find out non-homogeneous equation. So for non-homogeneous equation, dy by dx plus p of x into y is equal to qx. Now the coefficient of dy by dx is 1. We can see that. Then it can be reduced to exact by multiplying one integrating factor, which is nothing but e to the power integration of px dx. And if we multiply this, then we will get the solution of y as integration factor, which is nothing but e to the power minus integration of px p of x dx, then integration e to the power e to the power integration of px dx into qx dx plus constant. This is the solution y, and if it is in the form of dx by dy plus p of y into x is equal to q of y, then we will multiply this with integration factor e to the power integration of p of y or q of y into dy, and we will multiply this and we will get the solution as x is equal to e to the power integration of minus integration of q of y dy into integration of e to the power integration of q of y dy into r of y dy plus c. So for example, for homogeneous equation, so this function f of x y x square plus xy plus x square, this is homogeneous in order 2 because the highest order is 2. So if I substitute as x as kx and y as ky, then if we do this squared k square x square kx ky, we can write it in the form k square f of xy. So we can see the order is 2, or 2x minus y y prime or y dash is equal to x minus 3y. This is a homogeneous. How we will know this is homogeneous? Because we can write this y dash is equal to x minus 3y divided by 2x minus y. This is another example. This is different example. This is different example. And then this can be written as 1 minus 3y by x, taking dividing by x in this both side, upper numerator and denominator, divided by 2 minus y by x. So we can write this equation in the form of y by x. So this is a homogeneous equation. Now next is we will take an example how to find out if the given equation is exact form or not. To do that, we will equate them to 0. Then we know x dy plus ax plus y dx is equal to 0. How we get that? Well, y dash means dy by dx, so it will be x dy plus ax plus y will be multiplied with dx is equal to 0. After that, ax plus y dx, this term will be called as m, this term will be called as n, and then if we take the partial of m with respect to y, which will be equal to 1, and partial of n with respect to x will be equal to 1. This should be n. This should be n. So this should be n or x, because n is nothing but x only here. So we get this idea, and so this both of these differential are equal. So this equation is exact. So from this line we can see that this equation will be exact. Now the function can be written as mx dx and plus this function can be written as integration of mx dx plus zy. So integration of equation 1, this is the equation, integration of equation 1, because we know m of x is equal to x plus 1. Integration of equation 1 with respect to x, keeping y constant. So we will get a constant in terms of y. So if we do that, then we will get ax squared by 2 plus yx plus a constant, which will be the constant of z of y. Then we will integrate, we will differentiate this third equation. This is the third equation. We will differentiate this equation. So we will differentiate it. And with respect to y, keeping x constant with respect to y. X will be here a constant. Now if we do that, then what we will get, see the function with respect to y, then this will become 2 will be cancelled, and it will only left is on differentiate with respect to y. So this will become 0, because with respect to y this is just a constant. Then we differentiation of yx will be x with respect to y, and differentiation of z of y will be dz del z by del y. Now we already know this is equal to x. This is equal to x. So what we get is the partial of z with respect to partial of y is equal to 0. So the z is nothing but a constant c. So the final function will be ax squared by 2 plus yx plus. So why we and for this calculation, for finding out this f of x and y, we have used the first formula, the first equation, to integrate and then differentiating the result with respect to y. But we can do similar thing with the second equation also. First integrate this equation, then differentiate with respect to x. That will also give the same answer. Now non-homogeneous equation of this type. So this is also the same. We just there is a non-homogeneous equation that dy by dx plus p of x into y is qx. Qx is not equal to 0. That's why this is non-homogeneous. Now how to make it an exact equation so that you can find the solution? Well, we'll try to find out an integrating factor. So integrating factor will be e to the power this p of x. P of x is nothing but ax. So integration of e to the power integration of ax dx. A is a constant, so x squared by 2, ax squared by 2. Now we will find out the solution as e to the power and multiplying with integration factor e to the power minus ax squared by 2 multiply with integration of qx. Qx here it is bx. So b will be on the outside because it's just a constant. Then x integration vector e to the power ax squared by 2 dx plus c1. And if we put ax squared is by 2 is equal to t, so dt by dx will be just ax, because 2 will be cancelled after differentiation of x squared, 2x. So 2 will be cancelled. dt by a is nothing but x dx. So we can substitute x dx as dt by a, and we can put 8x square by 2 as t. So e to the power t, this will become dt, and outside b by a. So the answer will be integration of e to the power t is e to the power t plus c1, and outside also the function will be e to the power minus t. So e to the power minus t, e to the power plus t will become 1, and b by a plus c1 e to the power minus t. So minus ax square by 2. This will be the solution. So next we are going to discuss the second order differential equation. So uh, before that we need to know about linear dependence and what is linear independence. Now two functions are linearly independent if there is no uh, linearly connection between them, or in other words, if c1 and c2 are any two constant, and if c1 f1 plus c2 f2 is equal to 0, that will be only true when c1 and c2 both are is equal to 0. Or in other words, if there are lots of coefficients c1 c2 up to cn, and if we write down an equation where c1 f1 plus c1 f2 up to c n fn is equal to 0, this will only this will true only when all of the constants are equal to 0 simultaneously or individually. And the two solution of this two solution y1 and y2 of second order ODE, because in first order ODE we will get one solution, in second order ODE we will get two solutions. So the solution y1 and y2 of second order ODE are linearly independent if the Wronskian of y1 and y2 is not 0. If Wronskian is 0, then they are dependent. Wronskian is the determinant of y1, y2, y1 dash and y2 dash. General solution of second order ODE, uh, uh, let's take in general equation, d square y by dx square plus p1x, which is a function of p1 is a function on x, dy by dx plus e2x into y is equal to g of x. This is not homogeneous, so this is most general solution. So how we will going to find out? Well, if the roots of this equation are real and distinct, then solution will be y is equal to c1 e to the power m1 x plus c2 e to the power m2x. If root are equal, then the solution will be c1 plus c2 e to the power mx. If roots are complex root, then we will get y is equal to c to the power c e to the power alpha x cos beta x minus phi, or e to the power phi x c1 cos beta x plus c2 sin beta x. Now we can modify this, or we can say, like, if there is a differential equation which is kind of like this, right? Okay, let me show it. So if our differential equation is like this one, then what you can do, we can take we already know this is nothing but this is nothing but this is nothing but double differentiation. This is double differentiation. This is the first order differentiation. This is second order differentiation. And if we take x as is equal to e to the power mx, then if we differentiate it at any number of times, it will be in the first term it will be m e to the power mx, and in second term it will be m square e to the power mx. So if we m e to the power mx and m square e to the power mx, and if we substitute this in this equation, then we will get, if we substitute all of this value in this differential equation, then what will we get? We will get one quadratic equation, m square e to the power mx and k1 square e to the power 5x is equal to 0. There is no first order term. There is k square e to the power mx. Now we can take the common e to the power mx and m square, this will be equal to 0. So if e to the power mx is equal to 0, then these zeros are trivial 0. We are not interested in a trivial 0. What we are interested in when e to the power mx is not equal to 0. Now for that what we will do is m square plus k1 square we will equate it to 0. Then m can be written as plus minus another minus 1 k. So k plus minus ki. I means iota. I means iota. And I square means minus 1. Now if we substitute this, and then we will get the solution as e to the power alpha x, c1 cos beta x, and c2 sin beta x, like this one only, because what we get a complex root. So the solution is like this. Now when alpha is equal to 0 and beta is equal to k1, because in this equation we have assumed that this complex root is root as alpha plus minus I beta. Now but what we got here is I k1. We only got plus minus I k1. So alpha is equal to 0 and beta is k1. And if we do the substitution, then e to the power 0x is 1, so then it will be only, the solution will be c1 cos k1x plus c2 sin k1x. Now the second solution, second equation, which will be, so now we are going to study about differential equation which are in the form of z double dash is a function of z minus k square z is equal to 0. K is a constant, k3 is a constant. In differential form we can write it as d square of g square z of dz square minus k3 square of z is equal to 0. Now if we use y is equal to e to the power mx as a solution of this equation, and if we differentiate it twice and put in the place of z, then we will get a quadratic equation where the outside of this will be e to the power mx and inside will be m square minus k3 square is equal to 0. So the roots are plus minus k3. And if we use the equation y is, then it will be y is equal to c1 e to the power k3x plus c2 e to the power minus k3x. We already know that cos cos h k3x is equal to half of e to the power k3x plus e to the power minus k3x, and sin h k3x is equal to half of e to the power k3x minus e to the power minus k3x. Now if we use this cos h k3x and sin h k3x and sum it, then we will get half of e to the power k3x plus half of e to the power k3x, which will be equal to e to the power k3x. And if we use this in the formula, then what we will get is, and also similarly cos h k3x minus sin h k3x will be e to the power minus k3x. If we use it in our y is equal to c1 e to the power k3x plus c2 e to the power minus k3x, we will get y is equal to c1 cos h k3x plus sin h k3x plus c2 cos h k3x minus sin h k3x. And if we add, if we can common out c1 plus c2, then we will get c1 plus c2, take it as p, then it will be p cos h k3x plus q sin h k3x. Now next is finite Fourier transform. So here we have used the limit 0 to L for the Bn term. So it is in the finite Fourier transform, if we got a function which is f of x is equal to summation of n is equal to 1 to infinity, and Bn is a series, and then Bn multiplied by sine of n pi x by L. L is a unit in length, but it can be any variable. Now, how we can write or how we can find the value of Bn using f of x? So this is given by Fourier transform, where Bn can be written in terms of its infinite series, and it will be 2 by L integration of 0 to L f of x sine of n pi x by L dx. So the intuition is, if we have a function tx0 which is equal to summation n 1 to infinity, and it is written as pn sine lambda n x, which is equal to t1, then what can be the value of lambda n? So lambda n can be twice n minus 1 pi by twice L. So the value of the Pn will be 2 by L integration of 0 to L T1 sine lambda nx dx. So it can be written as 2 T1 by L, because T1 is a constant, and it will be integration of 0 to L sine lambda nx dx. And if we put lambda nx is equal, if we put now yes, if we put lambda nx is equal to t, then dt by dx will be lambda n, because lambda n is a constant, because we are differentiating in the terms of x. So dx will be dt by lambda n, and if we use dx is equal to dt by lambda n and lambda n x as t, then it will be 2 t1 by lambda n l integration of 0 to L sine t dt. And integration of sine t is minus cos t. Limit will be 0 to L, and if we use the limit and substitute the value of t, which is lambda nx, and value of lambda is twice n minus 1 pi by twice L, and take the limit 0 to L, and use the minus cos twice n minus 1 pi L by twice L, then we will get minus cos twice n minus 1 pi L by twice L plus 1. And we already know cos twice n minus 1 pi by twice L is 0 for all n. You can put n is equal to 0, then it will be if we put n is equal to 1, then it will be 2 into 1 minus 1, so half pi. So this 90 degree. So cos 0 is 1, cos 90 is 0. So for all value of n, cos twice n minus 1 pi by twice l will be by 2 will be 0. So that is why the answer will be only this term will be equal to 0. Only what left will be this term will be equal to 0. Only this term and multiplied with 1, this thing will left. So the answer will be 2t1 by lambda nl. So you can substitute the value of lambda n, which is twice n minus pi by twice l, and you will get Pn is equal to 4t1 divided by twice n minus 1 pi. So this was actually the value which we got in our earlier equation, if it is possible. So this is not here. I will show you in later term. Now Laplace in cylindrical coordinate system. So in cylindrical coordinate system, you will get this equation using first of all we need to solve this. This is the cylindrical equation, but if we can write it in terms of phi, in terms of r, phi and z, and then we will get the solution. But here let's leave it for now. Let's try to jump into the curved sheet dimension which occurs in atomic spectral line in classical dispersion theory and NMR theory. The function is f of x is equal to 1 by pi 1 plus x square. Then again there are transcendental function. Examples are log, trigonometry, hyperbolic. Now we are going to talk about the analytical function, and our next step will be analytical function. So a function is analytic at x is equal to x naught if it has finite value at x is equal to x naught. Mathematically means if it is not blow up, if you put x is equal to x naught, then if the function does not blow up or blow to infinity or minus infinity, then that function is analytic. If a function is analytic, it can be expressed as infinite power of series of the form of this equation, where we can write summation n 0 to infinity a n x minus x naught to the power n is equal to a naught plus a1 x minus x naught plus a2 x minus x naught whole square up to n, a n x minus x naught whole to the power n. Now for particular case of x naught is equal to 0, then example of analytic function can be 1 if the function is 1 by 1 minus x, then we can use the power series formula. Then we can write it as summation n 0 to infinity x to the power n is equal to 1 plus x square. We'll go up to n is equal to infinite terms. So this is an example for e to the power x. Then this is sin x, this is cos x. You can see it in here. Now the main some little bit more concept which is needed in order to understand the analytic function is ordinary and singular point. This let's take an example of second order ODE. This is a second order ODE y double dash plus px y dash plus qx y is equal to 0. This has an ordinary point at x is equal to x naught. And how we know that it has ordinary point? If the function px, qx, these are analytic, if px and qx at x is equal to x naught, then this equation has an ordinary point at x is equal to x naught, this differential equation. And it will have singular point when px and qx is not analytic at x is equal to x naught. And a singular point is said to be regular, and this singular point what we will get if this function is not analytic or this function does not give a finite value at x is equal to x naught, then it becomes a singular point, and with a singular it can be regular, where P of x and Q of x diverge at x is equal to x naught, but the limit when x tends to x naught, the x minus x naught of Px and limit x minus x tends to x naught, x minus x naught whole square, Qx remains finite. Then it will be called as regular singularity. Now, for example, let's take an example of differential equation, second order differential equation. Now, this is a legendary equation. It's a special equation. It gives some polynomial, which also the solution as polynomial, which can be called as legendary polynomials. Now, compare it with this equation. We can write it as P of x will be 2x minus 2x divided by 1 minus x square, and Qx will be n whole n minus n plus 1 divided by 1 minus x square. These functions are not analytic at x is equal to plus minus 1. If we put 1, x is equal to 1, then this becomes 0 and it will blow up to infinity. And if we put minus 1, it is squared. So again, x squared will be 1 and 1 minus 1 will be 0. Px and qx is not analytic at x equal to plus minus 1. But these are singular points. How? Well, if we take x minus 1 of px, then it will become 1, the lower n become 1 plus x, 1 minus x. 1 minus x, 1 minus x will be cancelled, and that the limit will go to, if we put x equal to 1, then limit will be 2 by 1. 2 will be cancelled, and it will be just 1. So the value is finite. So limit, however, the limit x at x is equal to plus minus 1 is infinity, or limit does not exist, but at x minus 1 p of x is finite, which is 1. Next thing is about the qx. So if we take x minus 1 whole square, then it will become x minus 1 whole square, then 1 minus x square. If we divide this, and we will get the function like this. And if we put x is equal to 1, separate this both of this term, then the limit will be 0. So x minus 1 is a regular singularity. X minus 1 is also a regular singularity. We can check this. Now, what is a power series method? We are going to discuss next is what is power series method. The basic idea of power series method is for solving ODE is about this ordinary point. So first, assume the solution of this problem as y will be the solution in terms of x. Y is a function of x, which will be in the form of summation 0 to infinity a n x minus x naught whole to the power n. Now, if x is equal to 0 is the ordinary point, so we obtain a power series in terms of x only, because x naught will be 0. So yx will be summation and 0 to infinity a n x to the power n.